Hello students, welcome to the YouTube channel of Padmabodh. The topic that we are going to cover today is ray optics, and this is going to be a theory session, and we are going to go through the basic theory of the chapter along with a few practice problems of the concerned formulas. Let us begin. So the first question is, what is ray optics? Ray optics is the branch of physics which concerns itself with the particle nature of light. Ray optics is the branch of physics which deals with the particle nature of light. You will also have another chapter called wave optics, which will be the branch of physics which deals with the wave nature of light. In this chapter, we will be treating light as particle nature. The second question that arises is, what is light? So light is the electromagnetic wave in which the electric and magnetic field vary harmonically in space and time. Light is an electromagnetic wave in which the electric and magnetic fields vary harmonically in space and time. You can also take notes along with me. One important point to know is that the visible light consists of waves with wavelength ranging from 4,000 Armstrong to 7,500 angstrom. So this is what we have covered in this slide. We got to know what is ray optics and what is light, and we also must know the range of the wavelength in which visible light lies. It is from 4,000 Armstrong to 7,500 angstrom. Now let us move on to the next topic, which is behavior of light at the interface of two media. What is media? You must have heard about medium. Media is the plural form of medium. So the first thing that would come to your mind is that, as we have learned in class 10th, that the light will bounce back from the surface on interface of two media. First of all, what is the interface of two media? Let's say I draw this line. Now this line is the interface. Why? Because on this side of the line, what I mean to represent is that here is air and here is, let's say, water. So air is medium 1 and water is medium 2, and they are two respective mediums in themselves, and the position at which they meet, the place which separates them, is known as their interface. So how does light behave at the interface of two media? Let us understand. So you might have guessed that the light will bounce back from the surface, from the interface of two media, but that is not the case. Actually, three phenomena take place when light falls on the interface of two media. The first one that you probably might have guessed is reflection of light. The second one is also what you could have guessed, refraction of light. And the third thing also takes place, which is absorption of light. Let us understand these three terms. So here I have drawn a diagram. Let's say that this green portion is medium 2 and the outer area, the air from which this incident ray is coming, is medium 1. Now the ray that is coming is known as the incident ray. Now the first thing that you do when you see an incident ray is see where it is landing. So this is the surface at which it is landing. Now at that very surface, the first thing that I will do is I will draw a normal. What is a normal? So let's say that this is some surface. Let's say this is a plane mirror. So I will draw an imaginary line which will be perpendicular to this surface at 90-degree angle to this plane mirror. When I draw an imaginary line perpendicular to the surface, it is known as the normal. Now with respect to this normal, the light will bounce back, which means that it came from medium 1 and it is returning to medium 1. That's it. That is an incident ray coming and it is reflecting back, bouncing back to the same medium. This is known as reflection of light. Now the second thing that happens is refraction of light, which means that this light does not bounce back to the first medium. Instead, it emerges into the second medium on which it is falling, but at some different angle. This is incident with respect to the normal at theta 1 angle, and it is refracting out through the medium 2 at some other angle. This is known as refraction of light, which means that initially it was on medium 1 and finally it is in medium 2. The third thing that happens is absorption of light. Yes, some of the light also gets absorbed by the medium, which means that it is not coming out. I can't say that it is bouncing back. I can't say that it got inverted into some other angle. It just got absorbed. So these are the three behaviors of light at the interface of two media. Let us dive deeper into the first case, which we saw, reflection of light. Now there are two laws based on this. The first law states that angle I is equals to angle R. The angle of incidence of light is equal to the angle of reflection of light. This is the first law. This law means that if I have a plane surface over here, let's say I have the mirror in which you look at yourself every day. This is the normal of the mirror, and here comes an incident light at some angle I. I'm going to call the angle of incidence with respect to the normal. With respect to the normal means that I am measuring it not from this surface, which means that I am not measuring this angle. I am measuring this angle. That is what it means to be measured with respect to the normal. So if it is I with respect to the normal, and if it bounces back at an angle r with respect to the normal, then angle I must be equal to angle r. That is the first law. Now, the second law of reflection states that the incident ray the reflected ray and the normal at the point of incidence all lie on the same plane. If you are not familiar with what is meant by a plane, then you might not get this point. Let me make it clear. So any flat surface that you see is known as a plane. For example, I have this envelope over here. This itself is a plane. It is a flat surface, and there are infinite planes in a space. So this position, the position of this flat surface is known as, let's say, plane 1. Now if I tilt it to some angle, this position of a flat surface is known as some other plane, say plane 2. So let's clarify this point further. Let's say that the surface of this board, the very flat surface of this board, is a plane that I am talking about. Now assume that this is an incident light. Here it comes. Now the very surface at which it has come, I will in my mind draw an imaginary normal. Let's say this is the imaginary normal and this is the incident light. Now these two themselves create a plane. Look, this is a plane. They both lie in the same plane. If I tilt it like this, then they both are not lying in the plane, but they are lying in one plane. Now when this light bounces back, let's say this is the reflected ray, then these both should also lie on the very same plane on which the normal and the incident ray were present. Say for example that the incident light comes like this, but the reflected light goes like this. I hope you can imagine what I'm trying to explain. So in that case the plane will become like this, because now they both are lying in one plane, which is different from this. So the incident, the normal and the reflected ray, all three should lie on the same plane, not like this, not like this, like this. That is what I mean by a plane. That is the second law of reflection. So that was all we had to know about reflection of light. Now let us come to reflection of light of plane surfaces. Now let us come to spherical surfaces. Suppose I have a glass sphere with me. It is a hollow sphere, there is nothing inside of it. It is just a glass sphere. Now say I cut it like this. This is a sphere, not a circle. It is a 3D sphere. And let's say I cut two portions out of it. One is this and one is this. Now I will do silvering on this side and on this side. Now silver polishing it from this side makes this side reflecting, and silver polishing on this side makes this curved surface, this side of the curved surface, reflecting. Let us understand the use of these. So we got to know that a spherical mirror is a reflecting surface which forms part of a hollow sphere. Now, in very simple words, if I try to explain, then this part of the mirror which we had earlier cut and this part of the mirror that we had earlier cut are given two names. This is known as a concave mirror and this is known as a convex mirror. When outside portion of the sphere is silvered, the inside portion of the sphere becomes reflecting. Similarly, when inside surface of the sphere is silvered, the outside surface becomes reflecting. This is a concave mirror and this is a convex mirror. You can note down the definitions of concave and convex mirror from here. Now let us jump into a very important portion of the chapter, which is the definitions related to spherical mirrors. Definitions in spherical mirrors. Now over here I am drawing the outline of the hollow sphere, the hollow glass sphere that I had earlier cut out my mirror from. Like I had said, it was about this portion from which I had. Sorry for the noise of the pen, let me restart. Let's say here I have the hollow sphere, the hollow glass sphere that we had begun our spherical mirrors with. I had cut a portion from here to get my mirror. This is my mirror. Listen very carefully, this is very important. Now I am going to draw a horizontal line from the center of the sphere. Now this is not a sphere. This is my mirror and I'm also going to mark the center of the sphere and connect it with these 2 points. Now I'm going to do the silvering on this side that I was talking about, which means that now this is the silvered surface and this is now the reflecting surface. So this portion that I have marked over here, I'm going to name it as P, and P is the pole of the mirror. As you can see, the pole of the mirror is the center. This is the curvature of the mirror, and at the center I have joined it with the center of this sphere, with this center of the curvature of the mirror. So this point is known as the middle, is known as the pole. Now the very center of the sphere that we had cut out our mirror from is known as C, and this is the center of curvature. I hope everything is clear till now. Now let me give these 2 points names. This is point A and this is point B. So the distance AC is known as the radius of curvature. As you can see that the sphere with which we had taken the mirror out, AC will be the radius of that sphere and it will also be known as radius of the curvature. Now the line PC is known as the principal axis. So the line passing through the pole and the center of curvature is known as the principal axis, and we draw this axis every time that we draw the diagram of a mirror. Now AB is the aperture of the mirror. AB. Let's say that I have this mirror. In that case, this distance would be the aperture of the mirror. Say I have this surface. In that case, this would be the aperture of the mirror. I hope you can understand what is the meaning of aperture. Now, this point is F. F is the principal focus. So, what is a focus? Let us understand. Say I take a concave mirror over here. I'm going to draw the principal axis always. Now I have a curved surface over here. If I polish it from here, now I know that this is a concave mirror. So let's say that there are incident rays coming onto this surface. It is important to show these lines with arrows. Let's say that these are the incident rays coming. Now what is important is that this point is P. So these rays should be parallel to the principal axis. This is the principal axis and these incident rays should be parallel to the principal axis. Now we have learned that it is a mirror. So the phenomena that will take place will be reflection, which means that the light will bounce back. You will notice that all of the lines will bounce back to the same point. All of these incident lines will bounce back to the same point. The very point is called as focus. So focus is the point at which the lines intersect, the incident lines intersect when the incident lines are parallel to the principal axis. Now let me explain it with a convex mirror. So here I have done polishing and now this outer surface of the curvature is the reflecting surface, which means that this is a convex mirror. Now I'm going to incident light rays onto this mirror, which will be parallel to the principal axis. Principal axis is the line passing through the pole, and you will see that all of these rays will appear to intersect at one point, which will be the focus. Now let us understand why the focus of a concave mirror lies here and why the focus of a convex mirror lies on the right hand side. So the thing is that focus lies on the side of the mirror on which the center of curvature lies. So if I'm talking about this surface, its center lies over here because it was the part of a sphere like this. So its focus will be on this side. If I talk about this mirror, it was a part of some this sphere. Sorry, if I talk about this mirror, then it was a part of this sphere. So its center lies on the right hand side, and for this mirror, the center lies on the left hand side. So the focus will lie on the right hand side and the focus will lie on the left hand side respectively. We can see that in the first case, the light rays came, went by, came, went by, and likewise, two, at least for now, two light waves actually intersected each other. We know that these are actual beams of light. So many beams of light collided together. So this got the name of real focus. Let's say I call it F1. So F1 is the real focus. It is real. And over here I can see that a real light came and it got bended like this. Why? Because it must pass from the focus. Now when the light came like this, I cannot just pass it from the between of the mirror, right? It has to bounce back. We are learning about reflection. So I turned it in a manner in which if I extend the reflected ray, I will have my line met at the focus. I know where the focus is. It is on the side of the center of curvature. I'm not saying it is the center of curvature, it is on the side of the center of curvature. So now I have bent it in such a manner that if I extend it in my brain, imaginary, this is imaginary, if I extend it, then it will meet at focus. So that is how I sent my beam of light. It came like this and then went away like this. So since this is just our imagination that these lines met at some point, F2 is not the real focus, it is the virtual focus. So that was all about focus. Now let us understand one of the most important topics of this chapter. If you get this topic wrong and if you have problem in understanding this topic, then you will not be able to solve the numericals of this chapter. This is very fundamental, very important, and if you do not understand it in the first place, which I'm sure you will, but if you don't, then you can watch the video again. So let us start. We are going to do Cartesian sign convention. We are going to learn how we measure distances while solving the sums of ray optics. So the first rule is that all ray diagrams are drawn with the incident light traveling from left to right. You will never by yourself say that, say this is the mirror and the light is coming from here. Why? It will not come because this is the reflecting surface, and usually in most of the cases we consider the left side of the surface to be, in case of spherical mirrors, reflecting. So we will always say that the incident ray is coming from the left hand side. And like you take in a number line, -1, -2, this side is taken as negative and this side is taken as positive. Very similarly, this is how I like to remember it. On the left hand side of the mirror, it will be negative. What will be negative? So the horizontal rays coming will be measured negative, and the horizontal lines on the right hand side will be measured positive. So this was the first point, that all the ray diagrams are drawn with the incident light traveling from left to right. Now the second point is that all distances are measured from the pole of the mirror. Let's say that this is my mirror and I have kept an object over here. Now from where will I measure the distance of this object from? I can see that this portion is also the mirror, this portion is also the mirror. So shall I measure this distance or this distance? These distances are always measured from the pole of the mirror, from here, not from here and not from here. So every distance that you will ever measure, say object distance, image distance, focal length, these are always measured from the pole of the mirror. Now the third point of the sign convention is that all the distances measured in the direction of incident light are taken to be positive. Like I have said earlier, that the incident light comes from the left hand side. The incident light comes from the left hand side and its direction will always be to the right. Did you get it? It is coming from the left hand side, so its direction is towards the right hand side, which means that any distance that is in the direction of the incident ray is positive. Although, how I like to remember is just easily every distance. Let's just say that the pole is the origin of the axis. So any distance on this side of the axis is positive and any distance on this side of the axis is negative. That is it. That is all you have to remember. So till now we had covered 3 points of the sign convention. Now the fourth and the fifth point are very simple. It says that this height, let's say A, B, will be taken to be positive and this height, let's say A dash, B dash, will be taken negative. It is just like your regular axis, x-axis, y-axis, x dash, y dash. This is taken to be 1 positive, this is taken to be 1 positive. Hold on. Yes, sorry. So this is taken to be positive, this is taken to be positive, this side is taken as negative, this side is taken as negative. Very similarly, from the pole this is positive, this distance is negative, this distance is positive, and this distance is negative. That was all about sign convention. It is very important. Now let us move on to the next topic, which is the mirror formula. This is the first formula that we are studying. So basically the mirror formula is 1 by f is equals to 1 by u plus 1 by v. This is the mirror formula. Here f is the focal length of the mirror. U is the object distance. V is the image distance. Let me show it to you pictorially. Say I'm taking a convex mirror over here. Now I place an object on this point O. I will consider a ray of light emerging from this object to this mirror. I'm sorry, I took a point object. This is the object that I take. It has some height, and now a ray of light will This is a convex mirror, and now a ray of light will fall at the surface of the mirror, and now it will go like this. It will form some image, and that image will form the image distance. Let's say that the image is formed over here. Now we know that this is the pole, so this will be U and this will be V. Where will its focus lie? Its focus will lie on the right hand side since its curvature is on the right hand side. So this distance will be F. This is the focus. So this is the distance of the object, this is the distance of the image, and this is the distance of the focus. So this formula gives us the relation between F, U and V. In this video, I am not doing the derivation of the formula, but we are going to solve some problems related with it. So first, what we learned is 1 by F is 1 by V plus 1 by U. And another thing that we need to keep in mind is that focus is the half of the radius of curvature. Yes, actually this formula is only for paraxial rays. So we consider this formula that F is equals to R by 2 only when the angle subtended, see what I mean, the angle subtended by these rays is very small. Let's say I'm talking about this ray. It is incident like this. Now this angle that it is forming is so tiny. So we are talking about these rays. These are known as paraaxial rays. So for paraaxial rays, only and only for paraaxial rays, the formula is that the focus is half of the radius of curvature. Another formula that we must get familiar with is that M is h2 by h1, which is equals to minus times V by U, which is equals to F upon U minus F. What is this? So let us understand what this is. Let's say I have a concave mirror over here, and this is the center of curvature. Right in the middle is the focus. So if I place an object over here, I know that its image will form over here, right? So this height, let's say A, and let's say that this point is I, this is B. So this height OA is h1 and this height IB is h2. Basically, h1 is the height of the object and h2 is the height of the image, the linear height. So magnification is the height of the image upon height of the object. Magnification, as we all know, is how much zoomed in or zoomed out the image is visible to us, right? If we want to write proper definition, then it is written like this, that it is the ratio, magnification is the ratio of the height of the image to the height of the object. Now this distance is the object distance and this distance is the image distance which I am measuring from the pole. So the negative of the distance of the image to the distance of the object is also magnification. This is a very fundamental ratio. Now by a very simple calculation, we get that magnification on simplifying this, we get, by using this formula, we get that magnification is f upon u minus f. This formula will be helpful when we only have values of m, u and f. If there has been any part of the video in which you did not understand what I said, please go back, watch it again, and then come, because now we are going to solve the practice problems. I have listed down all of the formulas that we have till now discussed, and now let us solve. So the first question is that an object is placed at 10 centimeter in front of a concave mirror of radius of curvature 15 centimeter. Find the magnification of the image. And the second part is when the object distance is 15 centimeter. Let us try to draw the diagram. Now it is said that it is a concave mirror. So here I will draw a concave mirror. Now it is given to me that an object is placed. I will take the object on the left hand side. So it is placed 10 centimeter from the mirror, and the radius of curvature of the mirror is 15, and I have to find out the magnification. So I have to find out the magnification. Now the two formulas that I know for magnification is this and this. It would be better if I used this formula for this sum. I have r is equals to 10 centimeter, isn't it? Tell me, is it right? Is the radius of curvature 10 centimeter? No, the radius of the curvature is minus 10 centimeter. Why? Because it is on the left hand side of the mirror. So I will take it as minus 10. It will never be given in the question that it is minus 10 or minus 20. They will only write the magnitude of the distance. So I will myself have to understand that if it is a concave mirror, then the radius must lie on the left hand side, and the object is always taken on the left hand side. So the radius of the curvature is minus 15 centimeter. Sorry, the object distance is minus 10 centimeter. Now I know that the focal length is half of the radius of curvature, which means that it is minus 15 upon 2. So it is minus 15 upon 2, and now I can put it into the formula that magnification is minus 15 upon 2 upon minus 15 upon 2, and then minus times minus 10. Okay, so you will be able to see it clearly now. This is what it is. We have put in the value of f, and minus times u. Now I will simplify this. Two से 2 is going to get cancelled, and this is going to become 5 minus 3. So the magnification is minus 3. That is it. We have the answer. This was the first part of the question, and now in the second part of the question, you can do it by yourself, in which you will take u as 15 centimeter. So do make sure to take it as minus 15 centimeter, because it is always taken on the left hand side of the mirror. You know the value of r, you can get to know the value of f, and then put these values into this formula. Now the next question is that a 5 centimeter long needle is placed 10 centimeter from a convex mirror of focal length 40 centimeter. Then find the size of the image of the needle. So first we are going to draw a convex mirror. Now a needle is placed, so the object will be placed on the left hand side. Its height is given to us as 5 centimeter, is placed 10 centimeter, which means that its distance is minus 10 centimeter because it is placed on the left hand side, and the focal length is 40 centimeter. So the distance of focus from the pole is given as 40 centimeter minus 40 centimeter. And now we have to find the size of the image of the needle. Can you point out the mistake that I made? Is this the question same as the previous one? The mistake that I did is I took the focus on the left hand side. Did it make you curious, or were you just following along? Since the curvature of a convex mirror is on the right hand side, the focus will also be on the right hand side, which means that it will be positive. Right? It will not be negative. This is not a concave mirror. In the previous question it was a concave mirror, and now it is a convex mirror. So the focus is positive. Now the height of the needle, which means that the height of the object is given 5 centimeter. We will take it as positive since it is standing upright. Now we need to find the height, which I will call h2, the height of the image. So do we know any relation between these two? Yes, this is the relation that we know. M is h2 by h1 minus v by u. So here we do not require magnification. Magnification is not mentioned anywhere in the question. So I am going to use the relation between these four quantities. I have h2, I have u, and I have to find, I have h1, I have u, and I have to find h2, and I have focus. So I can use the focus to find out the image distance, and then I will have all three of these values and I will find out the h2. So now let's do that real quick. 1 upon f is 1 upon v plus 1 upon u. 1 upon positive 40 is equals to 1 upon v plus 1 upon negative 10. We are going to send this 10 over here, and v is going to be 8 centimeter. Positive 8 centimeter means it is formed on this side of the mirror, right? So h2 upon h1 is equals to minus v by u. h2 is what I have to find out. h1 is what I know, 5 centimeter, minus times v, which we just calculated, 8, positive of u, which is given as minus 10. So minus minus is going to get cancelled. This, sorry, you were not able to see. h2 by h1 is equals to minus v by u. This is the relation that we are going to use. h2 is what we have to find out. h1 is given as 5 centimeters, minus times of V, which we just calculated as 8 centimeter over here, and now U, which was given to us as minus 10 centimeter. So this minus is going to cancel this minus, this 5 is going to cancel it by 2, this 2 is going to cancel it by 4, which means that the height of the image is positive 4 centimeter. What is meant by that is that if this is my convex mirror, then this is what my image looks like. It is upright and it is on the right hand side. Okay, so these were some of the very basic applications of the formulas that we discussed, and in the next video we are going to discuss further. Thank you.